What's up to you all pre-matriculants? Welcome to it. This is your favorite show, Learn Extra, with me, AB, and Dinyiko. I hope you're up and ready. You've got your notebook next to you. Your cell phone is logged on facebook.com/Learn Extra, and you are ready to learn more and learn extra with us. Mr. Dinyiko, how are you?
I'm good, and you?
I'm awesome. Say, it's a lovely Tuesday, and you know, it's physical sciences. It gets you active in a way.
Definitely, and I'm glad it comes on a Tuesday when it revives you. It actually brings you back to the vibe. That is physical
So, are you
sciences.
also not a Monday person? You love Tuesdays better than Mondays.
Look, yes, I'm a science person, so I am actually active in any day of the week, so whether it's a Monday or Tuesday, but I'm saying even if it's a Tuesday, I know some of the guys they are slumbering or doing whatever, but science will make you active.
Countering to that,
Yeah.
I love every day because I'm a mindsetter, so every day it is a lovely day.
That's great. Yeah.
But what are we doing today?
Well, today we'll be talking about gases. Basically, specifically, we'll be talking about the ideal gas. And before we actually come to talk about ideal gas, there's a lot of things that we need to put in place, and I will do that for them.
Okay, I guess the mindsetters won't be guessing some answers.
Well, yeah, we hope
because
for that.
we have a challenge question for them later on.
Yeah.
But otherwise, all you need, mindsetters, is to get your notes, view them, or download them. There are two options just for you. So all those notes will be available on facebook.com/Learn Extra. The links to those notes. And we have an awesome Casio calculator giveaway. So all you need to do is to keep your eyes on facebook.com, because that's where we're going to be having a lot of details and announcing last week's winner. So stay tuned.
Okay. That's it.
Let's do this.
Want me to take it on?
Yeah.
Good. Now, let's have a look at it. I said today we're going to look at this thing called the ideal gas. Now, the word ideal, people, means this is not something existent. This is not something that is there. It's something that we think about, we postulate. It's something that we define in our own minds, and given the reality, then we can go to it. So it's an ideal situation, ideal gas. That's what we're talking about. Okay, now in this lesson, for me to be able to take you to that level of understanding what an ideal gas is, we need to start here. I'm going to start you from the basics. I like making things easier for everyone. So let's go to the basics. So here I will start by looking at the definition of three states of matter. Oh, simple things, eh? Right? And of course, the physical quantities that are used to measure gases. Right? We'll talk about those things. We're going to describe the kinetic theory of gases. We will also describe the behavior of an ideal gas. Behavior of an ideal gas. So we want this ideal gas to behave in a particular way. So because it's ideal, we will actually place, limitations and things that will define it the way we want it to be. It's ideal anyway. Then we're going to explain the difference, of course, between an ideal gas and a real gas. Okay, because we have real gases. And also explain what we mean by the ideal gas law. So that's what we'll be talking about today. Now, here is the challenge question, all right? Now, I want you to put it down now, and as we move on in the lesson, think about it, try to work it out during breaks, and when you have got a little time to work on it, when you are at the same time listening to me, and attentively, of course, because you don't want to lose what I'm talking about here today. It says 4 grams of oxygen at a pressure of 150 kilopascals is sealed in a container. Calculate 1, the number of moles of the oxygen gas. 2, calculate the temperature of the gas in Kelvin. All right? So calculate the temperature of the gas in Kelvin, and the volume occupied by the gas. Okay, now one thing that has been missing here is actually the temperature in degrees Celsius. And what we have here is 25 degrees Celsius. Okay, so when you are to work out the temperature in Kelvin, you will know what to do. And of course, the last part will be to find the volume that this gas is occupying, right? So that is the challenge question. Summary, looking at the lesson itself, like I said, I'm going to take you, step by step, starting from the simple things. Going back to matter, we are saying that matter exists in different phases, and this will always depend on the temperature. We know that certain things are solid at certain temperatures, certain things are liquids in certain temperatures, and certain things would be gases at certain temperatures. So temperature becomes a very important factor in terms of what kind of a metal, of a meta state, okay? What kind of the state of matter that particular substance is going to have, when a temperature is at a particular level. The different states of matter have different characteristics. For example, let's look at the solids. We know that some substances are solids, and again, depending on the temperature. Solids have their own shape and volume, okay? This is a solid, okay? It has got a shape, and it has got a volume, okay? The volume occupied by this solid. Shape and volume together, there we have it for solids. But when we come to liquids, liquids would have their own volume, but they don't have their own shape. So they will always take the shape of the volume, of the container in which they are kept. So they take, if you have a liquid in this glass, for example, there's water in here. This water has got volume, all right? It has got volume, and where is the shape? It takes the shape of that glass because as a liquid it doesn't have a shape. If I bring in a rectangular glass here, because this one is cylindrical, if I bring in a rectangular glass here, this water will have a rectangular shape because a liquid takes the shape of the container in which it is stored. So that's what we are talking about when we say a liquid substance has got no shape, it has got volume. Next, we can have matter in the form of gas. Gases, on the other hand, they take the shape and volume of the container. So they, on their own, we've got no shape for gases. We also have no volume for the gases as they are. But if we want them to occupy a volume, we bring in a container, we place them inside, then they begin to have a shape. They will have a cylindrical shape because I've got a cylindrical container. I close it there, then they would have a volume, all right, of this particular container, which is cylindrical. If I bring in a rectangular one, okay, that would be or a cubic kind of a container. That's the kind of shape it would have. All right. When studying gases, we observe basically 4 physical properties. Now, this is very important because this is the basis of gases, and we need to make sure that we understand what this is all about so that we understand gases. Temperature. In everyday life, we measure the temperature of substances in what we call degrees Celsius. For example, the temperature of air. Then the temperature scale has 0 point as the freezing point. If we look at the freezing point of water, we say 0 degrees Celsius. But the investigations into temperature, into how substances would behave at certain or at different temperatures revealed that actually 0 degrees Celsius is not the absolute zero. There is an absolute zero temperature. That's when we bring in what we call the Kelvin temperature, or the Kelvin scale that we use to measure temperature, where the absolute zero and the freezing point or the melting point of water is 273 Kelvin. The boiling point of water at sea level, therefore, is 373 Kelvin. Why? Because with a degree Celsius scale above sea level, water boils at 100 degrees Celsius. So because the absolute zero, which is at 0 degrees Celsius, what we have is 273 Kelvin, it means you would have to add this to that to get to the boiling point. So that comes to 373. Now the volume, here we're talking about a quantity that is measured in terms of how much of the substance we have. Okay? The standard unit in which volume is measured is what we call the cubic meter, right? M to the power 3. It is common to measure volume in decimeter cube, all right, or liters too. So we need to know these things. 1 cubic decimeter is actually equal to 1 liter. You must know how to convert from different units of volume. That's very important. So we will learn as we proceed in this lesson how to convert some of these quantities. The third very important quantity that we need to know about gases is the pressure. With pressure is force applied per unit surface area. The SI unit for that is what we call Newton meter square, all right? Right, Newton meter or Newton per meter square, all right, because it's force per unit area. So Newton per meter square. So that should have been written like this. Pardon me for that. All right. And moving on, standard temperature. We do have standard temperature and standard pressure. Standard pressure is what we call the 101.3 kilopascals. This standard is equal to air pressure at sea level when water boils at 100 degrees Celsius, and may be called 1 atmosphere as well. So instead of saying, okay, the standard pressure is 101.3 kilopascals, you can say this is at 1 atmosphere. We can say that. So if you've got double of that, we'll say 2 atmospheres. That's what it means. Right. And the quantity of gas, and here we mean how much of the gas we have, and usually number of moles. If we're not talking number of moles, we will be talking the mass of the gas that we have. Okay, so that is the quantity of the gas that we're talking about here. Like I said, number of molecules or number of moles, or we'll be talking about the mass of the gas in grams. Okay, to explain the behavior of gases and how the physical quantities are related to each other, we use different models. Okay, one model will be talking microscopic things, you know, the small, very little things, minute things, and the other one will be talking macro things. All right, now when we're talking the microscopic model, we're talking the kinetic theory. That will help us to understand gases and how they behave, molecules, how they move and stuff. And a macroscopic, at the larger scale, the macroscopic model would relate to things of pressure, volume, temperature, and the number of moles, or what we call the quantity, like I said earlier on. All right. Kinetic theory, here we're talking about the theory that talks to how they behave, how molecules of a gas behave as they move. Okay, the molecules of a gas are very small compared to the spaces between them. This observation is based on the fact that gas molecules are compressible. So we need to know that they are compressible. To show that air is compressible, you can look at a tire, for example, of a car that can be pumped up by forcing or compressing gas into it. Molecules are in constant motion, okay? The molecules fill the container and spread out evenly, all right? Huge spaces between them, of course. And next, we also need to know that there are collisions between the molecules. all right, and also between molecules and the sides of the container. And these collisions, as we explain them, when we come to the ideal gas, there would be, we will say these collisions are actually elastic. We'll proceed when we come to that point. And the molecules of the same sample of a gas move at different speeds. It is therefore necessary to speak of the average velocity of the gas particles. And this average velocity of the gas particles gives us the average kinetic energy, which is related to the temperature. Okay? Temperature of the gas. I want to stop at that point for now, and we will proceed later on.
Thank you so much, sir. And Mindsters, keep your questions coming, and also your comments on Facebook, such as Sanele saying she's enjoying the show with her 11-year-old brother, as always. Even yesterday she was watching. So thank you, Mindsetters. Keep your questions and help one another on the page. We'll see you right after this break. Welcome back, my sisters. Now on the page, I can see that on the challenge question, you guys are not answering on the post. You must answer on the post that is on the wall, not on the inbox, but answer on the post for the challenge questions, so that we can see your answers. So the challenge question is on the page already.
Right, now let's move on. Let's go to the next section of the lesson here, where now I am moving you to the ideal gas. What is this thing called the ideal gas? Right. Now, the physical quantities of a gas, namely the pressure, the volume, the temperature, and the quantity of the gas, which is usually measured in moles. That small n there represents number of moles. All these quantities are related to each other by a simple law, all right? And we call this the gas equation. So this is represented by this equation here that says PV equals nRT, okay? So you would see here all these quantities are here. P for pressure, V for volume, N for the quantity of the gas, and T for the temperature. Now the question is, what is this R here? Now the R is what we call the ideal gas constant, all right? It's a constant, meaning that it remains the same at all times. It will be given to you. It is a value equal to 8.31. Don't worry about the unit for now. I don't want to bore you with a unit. This relationship would always hold true for an ideal gas. For that gas that I said we make it, it doesn't exist. And for that gas, these conditions here will remain the same in all situations. Okay, so under all conditions, this equation there would suffice. However, in reality, like I said, there is no such thing called an ideal gas. It does not exist. In this model, we recognize the following assumptions related to the kinetic theory. One, we are saying that if we have this ideal gas, its molecules have got mass, but they occupy no volume. So they don't have volume. It's an ideal gas. So we want to create it so that we will use that ideal situation to solve real situations. Okay. Two, the collisions, before that, this one, there are no intermolecular forces between the molecules of an ideal gas. Now remember, when we're talking intermolecular forces, what we are saying is that in all particles, whether we're talking things around us or particles forming substances like liquids, solids, and whatsoever, between those particles, there is always forces that are existing, okay? Forces that bring these substances together, or these molecules of a substance together. We call them intermolecular forces. Now, when we look at the molecules of an ideal gas, we are saying, let there be no intermolecular forces. In other words, let there be no force no force between any two of the molecules of an ideal gas. Let them not attract each other or push each other away. Let them just move at their own course randomly in whichever direction. Let them have no intermolecular force. That's what we are saying. Okay, and the collisions, now look at these molecules or imagine them. They are moving around in some container. There is no intermolecular forces between them. They move around, they collide with each other, they collide with the surface of the container in which they are kept. And we are saying let those collisions, let those collisions between the molecules of the ideal gas be completely elastic. Completely elastic. Now, what do we mean when we say a collision is elastic? We say that this collision, it happens, and by, naturally we would know that if there's a collision, what is likely to happen is that energy will be lost, especially that kinetic energy, because these molecules are moving. Now, when we talk of an elastic collision is a collision where the total energy, kinetic energy in particular, is conserved. So kinetic energy remains the same. So if this molecule had 3 joules of kinetic energy moving, this one had 2 joules of kinetic energy as they were moving. They collide here, they separate. They still have, if they had perhaps together it was 5 joules of energy. They collide, they separate. This might now have 3, this one would have to have 2. It can't have more than 2 or less than that because the energy has to be conserved, the total energy. So if it was 5 at the beginning, it still has to be 5 even after collision. But when you sum them, that's what we mean. When you sum those energies, that's what we mean. Okay, that's what we mean by elastic collision. So to emphasize it, kinetic energy is conserved in all of these collisions. All right. A real gas, on the other hand, now this is the one that is real, say nitrogen, say helium, say oxygen. This real gas will deviate from the behavior of an ideal gas under very low temperatures and very high pressures. Now, what does this mean? It would mean if we want to make a real gas to behave more like an ideal gas, which is the one that we are creating for ourselves, it means we would make this real gas, if we put this real gas under very high temperatures, and we also put it under very low pressures, the real gas will begin to behave like an ideal gas. That's what we mean there as well, if you want to reverse that statement. So if a question comes and say, under which conditions would a real gas behave more like an ideal gas? It is when the temperatures are high and the pressure is low. High temperature and low pressure would make a real gas to behave more like an ideal gas. Okay, now moving on. When the pressure of a gas is very high, like I was saying, its particles are very close to each other. And therefore, the forces of attraction between the molecules, which is what we call intermolecular forces, they become very big. And because they become very big, it means now the molecules are too close to each other. They are attracted to each other, much more than when the pressure is low. Remember, when we talk of high pressure, it's like you having a syringe and you are pushing the piston more into the syringe, and there's a gas inside, and the opposite end is closed, it's not open, then you are creating high pressure. All those gas molecules come so close to each other, and when the distances between molecules are smaller, the size of the intermolecular forces becomes bigger. Okay, so under very high pressures, we have got very big intermolecular forces. They become greater. The volume of the molecules gets closer to the volume of the gas. Under these conditions, real gases or real gas will change state, okay? Change state and become what we call liquids. Now, what does this mean? Earlier on, you might have had, if you grade 11s, if you watched the grade 10 lesson, you would have had John saying liquid oxygen. Can we have liquid oxygen? Yes, we can. That's when we expose oxygen into very high pressures at very low temperatures. And when we do that, it liquefies. Okay, so when we have high pressure and very low temperature, the real gases will liquefy, they will become liquids. On the other hand, this gas that we have created for ourselves, called the ideal gas, this one would never change its state. Whether you put it under very high pressures and low temperatures, it remains that gas. It doesn't change from being a gas into becoming a liquid, like we have seen with oxygen that can be liquefied. It doesn't undergo such changes. Okay. Now, lastly here, at low temperatures, which is something I have explained also earlier on, at low temperatures, the average speed of the particular or the particles of the gas is low, and the forces between the molecules increase. At low temperatures, therefore, real gases will liquefy. They will become liquids. Real gases behave like an ideal gas. So real gases will, there are situations where real gases will behave like an ideal gas, and I've said that earlier on. That's when you have got very low temperatures and very high pressure. Now, here, real gases behave like an ideal gas at room temperature and pressure. Now, what is room temperature? This is a temperature where, things normally would happen. When you are at home seated, we call that room temperature. It's normally around 25 degrees Celsius. So that is the temperature at which things happen. If we're in a lab, we would like to do things under those conditions, usually. So that's why we are saying we can use the characteristics of an ideal gas to solve problems that are based on real gases, because real gases will behave like an ideal gas at room temperature and pressure. Room temperature and pressure. I've explained the temperature, around 25 degrees Celsius. The normal pressure, as we see it, it's usually the standard pressure, which is 101.3 kilopascals. Okay, now let's use the remaining time to go back a little to this part here, which I feel I need to explain to you. Let's have a look at this one, the last part here. Remember, at this point, we're still talking about, this is what we're talking about, the kinetic theory of gases. Okay? The speed at which the molecules of the gas move will always depend on the temperature, okay, of that particular gas. Why temperature? Perhaps let me explain this. If you are at home, you want to boil water, put water in a pot, you don't want to, or even in a kettle, all right? Put it in a kettle, you switch it on, you want to boil the water. What you are doing, you are continuously changing the temperature of the water, starting from whatever temperature. Say the tap water was at, say about 21 degrees Celsius. You begin to boil it, changes pressure gradually. What happens as it changes temperature gradually? What happens as the temperature changes? You will see the water beginning to form the bubbles inside. And then the process of boiling is about to happen, and finally it boils. What does that mean? It means that before the energy was put into this water, the molecules were moving at a very slow speed. Now you pump in temperature there by pumping in energy, heat energy. Then the molecules absorb the heat energy, absorbs the energy, and the energy makes them to move faster now. And as they begin to move faster, it means the kinetic energy of the molecules also increases, okay? Because kinetic energy is the energy of motion, all right? Now, because you've got millions of molecules of that particular, of the water in this case, as I'm trying to demonstrate it, not all the molecules will have the same speed or will move at the same speed. So if you want to get the change in kinetic energy, actually we'll be talking about the average change in kinetic energy, all right? Because you'll be adding all the kinetic energies of all these molecules to find that average kinetic energy. And it is that kinetic energy that helps us to get to the level of how to get that particular temperature, the temperature of the water. The more the molecules move, the more they increase in kinetic energy, the more the temperature increases of that substance, in this case, water. Okay, so kinetic energy is related to temperature. Increase in kinetic energy of the molecules of a gas will result in an increase in the temperature of the gas. That's how it works. So that's the relationship between kinetic energy and the temperature of substances, in this case, gases. All right. All right, so that's what we have there. Now, another thing that I want to go back to as well and explain a little bit is the issue of the physical quantities of gases. Remember them? We're talking about temperature, we're talking about pressure, we're talking about volume, we're talking about the quantity of the gas. Now, these four lead to so many things. One, we have seen that it leads us to the gas equation. All right? It leads us to the gas equation. This one here. It leads us to the gas equation that PV equals to nRT. And we can solve so many problems using that. And even your challenge question, think about it. Okay, think about this equation here, how it can help you to solve it. So the equation brought the four quantities together. Another thing that we need to think about is, you would know that with gases, we've got laws that we're going to use to solve problems, and that will come in later lessons. But these four quantities are everywhere. You would have to relate the volume, for example, to pressure. We give it a particular law. We relate the temperature to volume, temperature to pressure. We give it a particular law. And that's how gases are actually supposed to be known when you are studying them. These quantities become very central to the learning around gases. Let me stop there. I'm going to give it to Abram now. And when we come back, we're going to look at some of the questions that we can use to try and see how much do we know about gases and what are those important sections that we need to know.
Awesome. And straight after that, we'll also be doing the challenge question answer. So I hope your answers are in already. But a big shout out to Kinetic and all the mindsetters, the grade 11s A at the Clip Town Secondary School. They are watching right now. A big shout out to you guys. And also a big shout out to Amkelan, who's watching the show with his mom, Promise Tembi Mashaba. We love you guys and thank you for tuning in. We'll see you after the break. Welcome back, Mindsetters. Now, the moment that we've all been waiting for to hear our winner of the Casio calculator from last week's show. And our winner is, drum roll please, can you go?
Oh, who can that be?
Richard Lebota. Congratulations to Richard Lebota. You've got yourself this awesome gadget. It is a lifetime gift ever. So, Mindsetters, stay tuned to Mindset to find out more about winning these awesome Casio calculators.
Great, thank you. Now, coming back to this, let's move on and have a look at our questions here, where we can try and improve our knowledge and our skills in solving some of these problems. Question number 1, okay? It says here, express the following in Kelvin temperature scale. And the first one that we have is 25 degrees Celsius, and the second one is 0 degrees Celsius. Now, let's come up with a formal way of doing this. When we talk of the Kelvin temperature scale, whatever temperature we're talking about is the unit of measurement is the Kelvin. So we use capital letter K for it. And the symbol for Kelvin temperature is capital letter T. Whilst for Celsius temperature, okay, what we have as the symbol for it is small letter t. And of course, we measure these in degrees Celsius. Now, converting from Celsius temperature to Kelvin temperature, we will always do it in this way. So Kelvin temperature, which is T, will always be the Celsius temperature plus 273. That is your absolute zero temperature. Okay? And that will give you your temperature in Kelvin. Now, what does it mean then for the questions that we are having? The first one is 25 degrees Celsius. So changing that into Kelvin temperature will be Kelvin temperature equals Celsius temperature plus 273. And that is Kelvin. So that will be equal to small letter t, 25 degrees Celsius plus 273 Kelvin, as a number now. And together they give us 298 Kelvin. So that is 25 degrees Celsius in Kelvin. Okay. And the second one is 0 degrees. So number B, we're converting 0 degrees Celsius into Kelvin. So T will be equal, capital letter T will be equal to small letter t plus 273. This should be easy to do. So we've got 0 plus 273 Kelvin, and that will be, so when I said Kelvin, I meant that when you have added everything together. So that gives you 273 Kelvin. Now, this is 0 degrees Celsius. That's right. This is 0 degrees Celsius. So it means that 0 degrees Celsius is 273 Kelvin. Now, this is what we call our absolute zero. Okay, this is absolute zero. Okay, now, okay, this means, I think I need to re-explain what I'm saying here, because I didn't say it as correctly as I should. Now, look, what I'm saying here is that it means that 0 degrees Celsius is not absolute zero in terms of temperature. Now, the absolute zero would mean it is the minus 273. From 0, you need to go 273 to the left to find absolute 0. So minus 273 becomes the absolute 0. So minus 273 Kelvin is the absolute 0 temperature. Okay, absolute 0 temperature. Okay, right. Now moving to the next one. Under what conditions does the behavior of a real gas deviate from that of an ideal gas? Explain your answer. Okay? Under what conditions will we see the behavior of a real gas? You know, saying to us, I am not an ideal gas, I am real, I exist. So which conditions will tell us that we are not dealing with an imaginary gas? Now, we said earlier on that when you have very high pressure, you are bringing the molecules very close to each other such that the intermolecular forces between them become effective. And you have got low temperature, okay? Low temperature. These two conditions will make your real gas to deviate, to say, no, I am not ideal. I am not imaginary. I exist. So I will behave in a different way if you have those conditions there. Right. 4 main properties of an ideal gas. Let's just write 3 that are more logical. The first one, we said that these molecules of an ideal gas have got mass but occupies no volume. Okay? So those molecules have mass and occupy no volume. All right? So the molecules have mass but occupy no volume. Occupy no volume. And 2, remember we said there are no intermolecular forces between them. We say with an ideal gas, with this imaginary gas, the molecules do not attract each other. So no intermolecular forces between the molecules. No intermolecular forces. There is nothing like that. Okay? Molecules, okay, occupy no volume, no intermolecular forces between them. And what else? What else? Who can think about the other one? Okay, quickly, molecules have mass but do not occupy volume, no intermolecular forces between them, and one very important condition or property or characteristic of an ideal gas, the collision or collisions between molecules. Between molecules and between molecules and the sides of containers. And the sides of the container are completely inelastic. So these collisions are completely inelastic. I mean completely elastic. Oh, sorry, what am I saying? Completely elastic. Now, remember what we mean by collisions being elastic? Remember that? We are saying that the kinetic energy is conserved. It does not change in the process of collisions. Kinetic energy is conserved. That's what we mean by collisions being elastic. Right. Okay. Let's see what we have here. All right. Now we come to our challenge question. All right. Remember the challenge question said 4 grams of oxygen gas at a pressure of 150 kilopascals is sealed in a container, and we said one thing that was missing here was temperature, and that was 25 degrees Celsius. Okay, and the first question here is find the number of moles of the oxygen gas. Now, I want to take you to some lesson that was done some months back, okay, with grade 10s, when they were looking at quantities of substances, number of moles. And this equation was introduced to you. Okay, so number A, number of moles, it's given by mass divided by the molar mass. Remember, with a small m, it's the mass given, and then the big M, it's your molar mass, all right? And in this case, the mass is 4 grams. So I will say 4 divided by, okay? So it's 4 grams divided by the molar mass of oxygen. Molar mass of oxygen, remember oxygen is O2, like that. So if I want to get the molar mass of oxygen, it will be 2 into 16, and that will give me 32 grams per mole. Okay, so this will be 4 divided by, this will be 4 divided by 32. Okay, so 4 divided by 32, and what do we get there? Let's just have a look. There is your calculator. 4 divided by 32. What do you get? 0,125. So you've got 0,125 moles. That's what you have there. Okay, and coming to number B. Number B it's asking us to have or to calculate the temperature of the gas in Kelvin. Now, the temperature of the gas in Kelvin, we have done that before. T is equal to T plus 273. Okay, that will be equal to 25 plus 273. Moving faster because we've done something very similar, if not exactly that. So this is 298 Kelvin. Then number C, we are to find the volume occupied by the gas. Now, how do we find that volume? To find the volume, we have to use the equation PV equals nRT. All right. Now, P is given to us, which is the pressure, given to us to be 150 kilopascals. Now, 150 kilopascals in this equation, P must be in pascals. So that will be 150 times 10 to the 3 pascals. Volume is what we are looking for. Number of moles is 0,125. We have calculated for it. Times 8.31, that is the gas constant, times the Kelvin temperature, which is what we found out, and that will be the way you will substitute everything there. Now, once again, when you have an equation like that, or what we call a formula like this, when you are asked questions, in this case, we are asked to find volume. We are to find volume. It doesn't help for you to make V the subject of the formula. It does, in a way, when you are smart and you want to put your values easily in there. But if you know that you're struggling with these numbers at times, The best way to do it is to look at the formula as is and you substitute like I did. And of course, substitute each and everything because this gives you marks. You get mark for that. Sometimes you find for everything like that, you've got 4 marks already. So when you work it out to find your volume, which you can easily get from here, then you have your answer in that way. All right. That brings us to the end, and as from me, Tinyiko Wakakosa, it's a very good afternoon, very good evening to you. Back to Abra.
Thank you so much, sir, and thank you to my ancestors that took part on the challenge question and got the answers right. If you didn't get it right, I'm sure you know now where you've made the mistake, and you can still fix it next time. But for today, that's where we end it. Thank you so much, my ancestors, and we're leaving you in peace.